as an analogy, just at the moment in here, the transmission protocol, one of the transmission protocols that I'm using is sound. That's the way that I'm communicating with you. I'm agreeing to use sort of sound. I could use sign language. I could just point to things on there and use sort of sight as a way of getting through it. But there's another protocol built on top of that, as well as the protocol of using sound for the communication. We agreed that I'm communicating in English for it. We agreed that I'm communicating at a certain speed. And as I mentioned last week, if I start to speak too quickly, perhaps people don't understand the protocol while I'm speaking, and some people can perhaps understand because they understand my accent, but other people who are perhaps from other countries won't necessarily understand what I'm saying. Some people, hopefully you got all that. Some people want to, but particularly if English isn't your first language, you can't sort of, so there's an agreed protocol for speeds of transmission, modes of the actual ether that it flows through, and the protocol inside it. Another aspect that we're looking at here is the operating system. What operating system is resident on that node device? So you've got a node that's running, and an operating system needed to be able to say run software on it. Now, I'm not going to go over the whole thing about what an operating system is. Hopefully, say you'll have done parts of that either in your first year or with science, you'll have done quite an amount on it. But basically, an operating system is giving you the ability to run software for a user, or software to control the device itself. It needs to be able to interact with the hardware, to schedule tasks and prioritise one over the other, mediate between different applications that are competing to use memory resources. And we're all used to operating systems on things like your Windows and your Mac and Linux. They've got their own operating system, but the requirements for, say, Windows 10, they say, well, your PC must have something like at least 2 gigabytes of memory available to be able to run this. And yet, when you look at some of these other devices, he said, I'm just trying to quickly find the other one. Bear with me a second. Last week, I came out with this sort of sample node. This is sort of one of them. This is just like a standalone one with a description of it. This was one from this Advantix system. And this comes with a memory of 1 megabyte, 8K of data RAM, 116K of RAM. I mean, are you going to fit Windows 10 in that? Not even a chance. You can't even get one fraction of it. Even something with a smaller footprint like Linux, you're not going to get in there. So basically, a lot of these nodes that are running on these devices won't be running that operating system. One, because they can't. They've just not got enough memory, processors sort of not good enough to do it. But also because you don't need it. You don't need Windows 10 on one of those little environmental sensors, or on that little that little clicker button that I sent around the other day. They don't need all that full-blown operating systemness bit. So I'm just trying to get back to my original one now. So whilst an operating system may be there to do a lot of these sort of general ideas, memory management, power management, networking, programming environment, sort of giving access to sensitive resources, a whole sort of series of things that an operating system sort of does, providing all these sorts of types of services. And again, not too interested in the whole sort of range of what an operating system is. But basically, you can't run things like Linux, Windows and the like on one of these. Yes, if you do something like intermediate, like a Raspberry Pi, then you can run a fairly low-grade operating system on that. You can load Linux up on a Pi, no problem to it. But a Pi's got sort of gigabytes of memory available to it. In general, these sensors are really just sort of tiny old processors with almost no hardware available to it, no memory sort of available to it. And so we have to have operating systems that are built for that. And that's where things like TinyOS come in to it. They're operating systems geared specifically for low-grade devices for it. And they do very, very restricted applications to it. You couldn't run your games on these sorts of things. They only run tiny, tiny applications for it because they're embedded on small pieces of hardware and have a very small footprint to it. They typically don't run many languages. They'll normally run a sort of C-type language, and even then it's a cut-down sort of version of it. Now, fortunately or not, we don't generally have to write these. We as application developers, we buy in the sensors. So we buy in one of those white boxes that's got that software written on it. It's got its operating system on there. Somebody's written all the interface between the sensors and being able to sort of send the things out. The sort of thing that you're doing in the labs, you're creating nodes in the labs, talking in your Java to your slider, to your temperature sensor or whatever, and sending it out. That's the sort of code that needs to then be shrunk down onto one of these sort of tiny sensor devices. And what you'll normally do is you'll build up a conceptual model as an application designer and say, right, this is conceptually what I want. These are the sensors, and here's the sort of software to do it. And then we'll give it over to electronic engineer and just say, shrink that, will you? Whatever, and sort of get the code running on a much smaller system, and then put it in, get the product design people out to put it in that nice white plastic box or whatever. That's where it involves getting your backers in to perhaps sort of build these things. You're off on Kickstarter to sort of do these things. So yeah, TinyOS, completely what we call non-blocking, which makes it a bit of a problem in some operating systems. It can't block other sort of processors in. Now, a lot of these sort of terms won't really mean so much if you're not sort of that familiar with sort of operating systems, but the general idea being you can't do too much for it. About what there's in there. There's no things like virtual memory, no dynamic memory allocation, no exceptions, no process management, only one process at a time. All the sorts of things that we've been building into operating systems for years have just caused them to bloat and bloat and bloat, to get bigger and bigger, to be able to do bigger things. Here we're having highly specialised machines to strip down the memory size and then the sort of system overhead to sort of get out of it, to cut down on the sort of power usage. Because quite often what we want is for the sensor to get the job done and then go into sleep mode or sort of temporary sort of stop for a bit. I will see the networking technology that you use can have a big effect on that, particularly if you use things like Bluetooth over Zigbee. Just as an aside there, like if you use a Bluetooth device, how long does it take for your Bluetooth to recognise another Bluetooth device in the room? It does its pairing 2 or 3 seconds to sort of do that. Whereas Zigbee, it's measured in milliseconds, so the thousandths of a second to establish a connection and send the data up. Zigbee wakes up instantly, whereas Bluetooth takes 2 or 3 seconds to wake up, which might not be too much for you. You can afford 2 seconds, something like that. But if something's sending data and having to go to sleep every 5 seconds, if it's broadcasting data out every 5 seconds and it takes 2 seconds to go to sleep and wake up, then there's a lot of overhead in there sort of going out of it. So we need operating systems that work extremely efficiently for that, to sort of wake up and then go back to sleep again and manage your power for it. And as I say, TinyOS is one built around that. There's another one, Contiki. TinyOS was built originally for before we really sort of came across this sort of Internet of Things. It was built for very sort of specific processors. It was built for engineers to work with. Whereas Contiki was a similar sort of approach to it, an open source operating system, more aimed at wireless sensor networks and what its configuration was. So a typical config needs about 2K of RAM and about 40K of ROM. So not a huge amount, less than 50K of memory. Well, that's nothing. That's absolutely nothing for it. Totally sort of minimal. But what it provides as well, what sort of IP communication does it provide to sort of get round? Now, yeah, I'm not going to go over, as I say, all the bits about the full sort of readings of it, but if you sort of want to have a look about what the background is of some of these, it can sort of help broaden your understanding of it. But we don't need to know a lot about that level because we're writing applications above that. It'd be a different matter if I was talking to electronic engineers who are building these sorts of things or writing software actually on the node itself. But at some point, you're going to create these conceptual models. You're going to have to talk to an electronic engineer to build these. So it's as well to be aware of what the capabilities are of the device that you're sending it out to.